Swayam Prabha. Digital India. Educated India.
Welcome back to another lecture of control systems. So in the last lecture we saw how you can model rotational mechanical systems, and then we wanted to take an example which combines all of the knowledge that we've acquired about modeling mechanical and electrical systems through the means of armature controlled DC motor, right. So we want to model this mathematically and put in all the knowledge that we've acquired thus far to good use here, and hopefully this example will serve as a very good test case. So we had discussed briefly how we can capture a schematic of this system here, and the goal was to obtain a transfer function between this theta on the motor side to the armature voltage, which is my input, or the speed of the motor side, which is omega m, it's big omega, to the armature voltage. All right. So let's see how we can get about this. The first thing is, of course, we can write the equation of this side using KVL. What is KVL? So KVL is going to tell me that it's VA minus VB is equal to IA times RA plus SLA. Okay, this is going to be my first equation. All right. What's going to be my second observation? I know that this back EMF VB, the exact expression for a DC motor, it can be given by P phi Z N over A, where P is the number of poles of the motor, phi is the flux per pole, Z is the total number of conductors, N is the speed in RPS, and A is of course the number of parallel paths, which depends on the type of winding, whether it's a lap winding or wave winding. So I invite you to revise your electrical machines course if you haven't already, right. So the take home message here is, look, this phi, this flux is proportional to IF, but we've already said in the previous lecture that this is not a field controlled motor, this is an armature controlled motor, so the field current is held at a constant. So therefore this phi is a constant. You can clearly see that the P, the Z and the A, these are also physical constants, yeah. So all that varies here is basically the speed. So we can actually write the VB to be proportional to the speed, which is nothing but omega ms, all right. In other words, this is nothing but KB times S times theta S, okay. So this is going to be my second equation, all right. So I hope that this part is clear. This is coming from our understanding of electrical systems, remember, nothing to do with the mechanical part that we've learned in the preceding lectures, only the electrical circuit. This is just KVL and the fact that we know this about an electrical machine, a motor, a DC motor. This comes from your domain knowledge of electrical systems. What about the next equation? All right, the next equation would be the mechanical equation. What are we going to do? Let's reflect all of this assembly onto the motor side. We know how to do that. Just multiply this GL by the square of the gear ratio. By gear ratio I mean Nm by NL. Remember, this is the destination, this is the source. So Nm over NL is the destination upon source, so squared. So Nm upon NL whole squared times GL. Same thing you do with D, right, and then you balance out the equation, the torque balance equation on the other side. alright. So what do we do then? So clearly you see that if you can write this as, let us say the Tm, have I written as Tm? Okay, I have not written anything here. So let us say this machine, there is a Tm here, the torque on the motor side. So this torque on the motor side, so often I am going to drop this argument as I usually do. Right now let us keep it for the time being, later I will drop it. So this TMS can be balanced by what? Look, there is already some inertia of this shaft on this side, okay. So that remains as it is. There is also some damping on this side, yeah. There is also some damping on this side. So that remains as it is. What gets added to it is the reflected part. So we will have Jm plus Nm upon Nl squared times Jl, right, times S squared, and then we can write theta m s, right, plus again the damping that was already existing. So remember, now you have inertia and damping on both sides. So this inertia is basically due to the weight of the shaft itself, okay, whatever is there on the shaft. This shaft can be pretty hefty, yeah, and there could be some damping of that rotation as well on this side. So this is occurring due to natural reasons, yeah. This on the other hand could be a load, the inertia of the load, but this Jm is basically the inertia of the motor itself. The motor, the shaft, the armature, everything combined together gives you some inertia, right. So that is the Jm. So all that you need to do is keep the Jm on the secondary side, this will be intact, so the Jm remains intact. Whatever is being reflected from this side, that is the only variable that gets transformed through this gear ratio. It is exactly like in a transformer, no. Then you have Nm over Nl whole squared times d, let me call it dl, and this times s theta m s, right. So we can call this as our d equivalent, we can call this as our j equivalent, and kind of try to simplify stuff. Let us do that. Let us not keep this very cumbersome, because anyway we are going to come across very hefty equations later on, okay. So let us call this equation number 3. Where does this equation come from? Yeah, where is this equation emerging from? This is emerging from your knowledge of mechanical systems, purely mechanical systems, the rotational mechanical systems with gears that we just learnt in the previous lecture, yeah. So notice, keep track of this. This came from the electrical system, knowledge of electrical systems. This came from the knowledge of mechanical systems with gears, rotational mechanical systems with gears, and finally the icing on the cake is going to be the electromechanical part, how we can club together, how they are coupled together, yeah, and that is given by how this torque is obtained. So what is this torque after all? This is going to be nothing but proportional to, you know, again the flux in the armature circuit and the flux in the, this is going to be proportional to the armature flux and the field flux, but again this field flux is constant, because If is constant, right. So what we can then write is that Tm is equal to some Km times, notice that this flux in the armature, what is this proportional to? I have not mentioned this, so let us take a brief excursion into this. So what is this flux proportional to? Remember, you had total ampere turns Ni divided by something called a reluctance. So in your magnetic circuit, if you recall, this reluctance, yeah, this reluctance was given by some physical parameters, no, L over mu A, where L is basically the length of the magnetic path, A is the cross sectional area, and mu is the permeability of the medium. These are all physical constants. So it turns out that this flux is proportional, and N is of course the total number of turns. So this flux is proportional to the current, yeah. We saw that this is proportional to H, you know, in electromechanical systems. We have seen this electromagnetics, haven't we? From basic principles of electrical engineering, we know this. This is called reluctance, this is the flux, this is the ampere turns, right. So therefore it turns out that this flux is proportional to nothing but the current. So what is this armature flux going to be proportional to? It's going to be proportional to the armature current. That's all there is to it. So this is the bridging part of the equations, electromechanical, okay. So we've seen one part of the equation, these two equations come from understanding of electrical systems, this equation comes from an understanding of mechanical systems, and this bridges the gap between electrical and mechanical part. Yeah, the torque is proportional to the armature current, right. So now we are in a position to obtain our transfer function. What is the first thing that we do? Let us quickly write down theta ms upon Tm, yeah, from 3. This can be written as, of course, 1 by J equivalent S squared plus, yeah, D equivalent S, right. So that is, let us say, Roman 1, all right. The second equation is, now we want to find out this Tms divided by VAS. How do we do that? So what you can then do is, you see here you have an equation that contains IA, isn't it? So my suggestion is that as IA we can replace by T upon Km, right, and replace, so plug in. So what we then do is, we plug in this relation here and we substitute this IA as Tm by Km, and then in equation 1 what we have here is, yeah, let me just write it down because I have it worked out, so I can write it easily, but I urge you to check this. So this is going to be nothing but 1 divided by Ra plus Sla upon Km plus Kb. What is this Kb? Recall, this Kb is the proportionality constant in this equation, where it tells you that the back EMF is proportional to the speed, all right. This is Kb divided by, of course it was Kbs divided by J squared plus ds, so one s cancelled out, so it was J equivalent s plus D equivalent, all right. Okay, so now that we have got these, let us call this Roman 2. Now observe that 1 divided by 2 gives me what on the left hand side? 1 divided by 2 gives me, or rather, sorry, not 1 divided by 2, 1 multiplied by 2 I should say, isn't it? Yeah, I suppose so. So 1 times 2 gives me what? You see, this is theta m by Tm, this is Tm by Va, and remember what my goal was, right? Remember what the goal was? The goal was to obtain theta m upon Va. So I will get exactly what I want, what I am looking for, theta m by Va, if I multiply 1 and 2. So I am going to do that, and I am going to get, leads to theta m by Va given by something like Km upon S times Kb Km plus Ra plus Sla times J equivalent S plus D equivalent, all right. Now I am going to make another assumption. What is that assumption going to be? The assumption again comes from my understanding of the electrical circuit. I am saying that in the armature circuit, which is basically this circuit, we have, and it is a reasonable assumption to make, we have that La by Ra is very, very small, right. So the ratio of the inductance in the armature circuit is way smaller compared to the resistance in the armature circuit. So for all practical purposes we can probably ignore this L, right. So if we do that, let's quickly do that. What then happens is we are just left with an Ra here, right. So then we have theta m by Va. Remember, this is an assumption, this is not an exact thing, okay, this is an assumption we are making, so we are ignoring this La compared to this Ra, so we are going to just let this tend to 0. Then what we have is Km divided by, you can just check my calculations, divided by S times J equivalent times RAS plus RA times dE plus KB Km, which we want to write in a simpler and better form as Km upon J equivalent RA divided by S times S plus, let us say, D equivalent upon J equivalent plus KB Km upon J equivalent Ra. Okay. So, let us call this alpha, let us call this K, then we have the transfer function look something like K upon S into S plus alpha, the abstraction. Okay. But remember, even though this might look like the end of the story, there is something more that needs to be done here. What is it? As part of a control engineer's job, it does not end with just giving this mathematical model. You have to also be able to determine these values, these numerical values of this physical parameter. You just say this is K by S into S plus alpha. What about K? What about alpha? Unless you know what alpha is, unless you know what K is, you will not be able to find out the response theta for a given Va. You will only be giving some algebraic symbols, right, which may not be good enough. I want to find out how fast, for example, this response due to a step input decays and so on and so forth, which we will obviously see very shortly when we get into the analysis part. But then this is not good enough. So, there must be some way I must be able to determine these physical parameters. So, what are my unknowns here? My unknowns are this, if I can determine this Km by J equivalent Ra is equal to K, and if I can also determine, yeah, so if you notice this, if I can determine this Km by J equivalent Ra, this also appears here, and if I can determine this Kb, and if I can determine this Kb, then at least I will know this part and I will know this part. Then what remains is this Deq and Jeq. Of course, this I can measure mechanically, by a dynamometer experiment, or these can be calculated from the mechanical knowledge of the mechanical system. Okay, but at least from the electrical side, how am I to determine these systems? Now, for that, you notice another observation here is, of course, you have Vas is equal to Kb times omega S plus Ra times, of course, we have assumed that this inductance has been already ignored. Okay. Now, if you look at this time domain equivalent, this Vat is equal to Kb theta dot t plus Ra Tm upon Km. Now, this is basically the speed torque characteristics of a DC machine, which can be evaluated. So, you can see that the speed torque characteristics for a given voltage, it is a straight line. So, if you fix this side up, this is basically nothing but a straight line, it is y is equal to mx plus c. So, for a given armature voltage, this is going to be a straight line where your x axis is going to be the omega, yeah, this is theta dot is nothing but omega, and the y axis is going to be the torque. Now, notice interestingly what happens here, right. So, what can I say about this? So, for example, now if I am holding the motor to a standstill, okay, which is when it is stalled, okay. So, when a motor is stalled, then this omega is 0, right. So, for a given voltage, for a given armature voltage level, yeah, I can then obtain this, can I not? Yeah. So, from this TA plot, what can I get? I get that the T stall or the stalling torque is given by VA T. Of course, if I can fix up this level, then I can get rid of this. So this is a curve for a particular VA. So let's say this is VA1, then you have another, this is VA2. So these are speed torque characteristics of the DC machine under consideration. Okay. So this is VA1, VA2. So suppose I have fixed up some VA. Then what I have is the stalling torque. Okay. So suppose I have forcibly held the armature frozen. I have applied a small voltage, a test voltage, and I have forcibly held the armature frozen, right. So then if I can measure the stalling torque using a dynamometer, right, then what do I get here? I will get Km by Ra. Now remember, this is coming from my dynamometer measurement, this is what I already know because I have held this constant, so therefore I can compute this. So then this can be computed, alright. On the other hand, suppose now you are running your motor at no load, alright. If you are running your motor at no load condition, what do you then know? If you are running your motor at no load condition, then the torque vanishes. So then what you have is omega no load is given by VA by KB. So remember, this again you can measure, you have equipments to measure the no load speed. Of course this is the voltage that you are applying, so this is known. So then KB can be computed. So then what happens? You see, I know this ratio, I do not know individually what Km and Ra are, but I do not need that in order to compute K. So I have found this ratio, I have found this variable, of course I can measure J equivalent and D equivalent. So then in the preceding transfer function I know each and every individual term, so I can actually give numerical values for K and alpha. That is what I was looking for, and that completes the entire modeling, the entire job of modeling this system for a control engineer. Okay. So unless you have gone this far, the job is not over. So you have to be able to design some experiment, staying within the constraints of the physical parameters, of course. You have to be able to design some experiments which will enable you to compute all of these things, alright. Unless you do that, just merely saying that this transfer function looks something like K upon S into S plus alpha is not good enough, okay. And why that is not good enough is exactly going to be the topic that we are going to see next, where we will study the transient response of physical systems. In particular, we will study the transient responses of first order and second order systems. Before we get there, here is a brief discussion on some other important topic which I feel you should be aware of as control engineer. So with that, let me formally announce here that we are coming to the end of the modeling part. Again, to reiterate, this by no means should suggest to you that this is all there is to modeling. In fact, modeling itself can be a very challenging part of a control engineer's task. So please be respectful of physical constraints and conditions when modeling systems. Try to acquire domain knowledge, that is the key to all of this, okay. So let us see something interesting now. We will move over to the next topic, which is analysis or transient analysis. So how the transient behavior of dynamical systems are governed or dependent on the locations of poles and zeros, okay. We shall next see that, and in particular we shall see the step responses or the transient step responses of first and second order systems. Standing assumption is we are only going to be looking at stable systems which eventually acquire some steady state value. You see, if systems are unstable, they do not acquire any steady value, the system responses blow up, they are unstable, we have seen that, right, in an earlier lecture. So in summary, what we are going to look at is the assumption is going to be thus: all the poles of the system are going to be on the open left half plane, or at best on the imaginary axis, but not repeated, okay. So that is the kind of systems we are going to have under consideration, and subject to that we are now going to look at the transient responses. But before that, as I promised, here is a brief discussion on something a bit different, although not completely uncorrelated with what you are going to do. Now remember, when you are given a transfer function like this, say s cubed plus s squared plus 3s plus 4 over, let us say, s to the power 4 plus 5s cubed plus 7s squared plus 8s plus whatever arbitrary values you can give. Yeah, you can immediately map in your head this transfer function to the following differential equation: y4 plus 5y third derivative plus 7 times second derivative of y plus 8 times first derivative of y plus 5 times y is equal to third derivative of the input plus second derivative of the input plus 3 times the derivative of the input plus 4 times the input. Immediately you can map this, right? We have already seen, we are already too familiar with this. Now remember, we talked about the zero input response and the zero state response of a system, right? So if you want to find out the zero input response, we basically ignore this part. So that is the zero input response, and we just look at the response due to initial conditions, non-zero initial conditions, right? Similarly, when we are considering the zero state response, this transfer function suffices. So we assume that all the initial conditions are 0, right? And we just say that we look at y of s is equal to g of s times u of s, right? Notice that when you are writing it in this fashion, let us say this transfer function g of s has 4 poles, say p1, p2, p3, p4, right? And this u might also have some other poles, let us say alpha 1, alpha 2, I do not know how many. Yeah? So this u, this input in general might have, let us say, 3 poles, right? Now if you are trying to find out y of t, yeah, you are basically going to take a Laplace inverse of this whole thing, not just gs, but you are going to take a Laplace inverse of gs times us. So if you write this, you will see that it will come as 2 parts, summation ci e to the power pit plus summation di e to the power alpha it, okay? And this is where we distinguish between something called, so this is the so called natural response of the system, and this is the forced response of the system. Now why I want to make a subtle point here is that you might be misled into believing that the zero input and the zero state are very straight away related to this natural response and the forced response, in that you might say that the zero input response is nothing but the natural response and the zero state response is nothing but the forced response, but that is not actually the case. There is a difference. Why does this difference arise? So in a question, for example, in an exam or wherever, people might ask you, solve for this differential equation that is given to you. For example, let us say a differential equation like this, and then decouple the zero input response and the zero state response, okay? So we have already seen how to do that. Another question could be, solve for this differential equation and decouple the natural response and the forced response. Now the former solution which you obtain, where you decouple this zero input and the zero state part, will not be the same as this decoupling between natural response and forced response. How so? I am not going to go into the detailed solution, but I am going to just discuss briefly, and I hope that you give it some moment's thought and you will understand. See, here is how it is different. Look at these terms, these natural responses. Suppose in this differential equation all your initial conditions were 0, right? So you are looking at basically the zero state response, right? If you are looking at the zero state response, yeah, if you are looking at the zero state response, so I think I should also say here, I have missed a bit, so you will also have some Laplace inverse of some initial condition, some y0 related terms, and we will have some denominator here, right? So that is going to lead to this sum, right? Sorry, I missed that. So this should have also been because now if you are writing the complete solution, you are not just writing the solution due to the forcing function, but also due to initial conditions. So this is a total solution, this is a y complete solution. So again, to reiterate, now notice what happens. Now with this in mind, now notice, now suppose you consider all your initial conditions to be 0 here. So then you know that in our natural parlance, this parlance, we are basically dealing with the 0 state response. So it is basically all the response that is due to the externally applied forcing function, but that is not the forced response. Why? Because the forced response is only those modes which arise out of the poles contributed by the input. Okay. But remember, even if you are considering your initial conditions to be 0 and you just have a forcing function, when you are taking the Laplace inverse of this, it will contain all the modes, not just the modes or not just the response due to the poles contributed by the input, but also the response due to the poles contributed by the system itself, and these will come as part of the natural response, not the forced response. So in other words, if I am to summarize this, you can write y as y forced response plus y natural response. You can write this as y 0 state plus y 0 input. Okay. But do not make the mistake of thinking that the y natural is nothing but the y 0 input and the y force is nothing but the y 0 state. In other words, what I can say is that remember this y f, yeah, this y f will be only a part of the 0 state response. So y f is only a part of course very loose notation here, ys is only a part of the y 0 state, okay. So only those parts of the 0 state response, yeah, only those parts of the 0 state response which are exclusively due to the modes of the input, that is alphas, yeah, they will qualify as yf. On the other hand, y natural only contains the response due to the modes of the system, that is the PIs, the natural response, okay. But some part of the 0 state also contains, remember, even if you have zeroed out all the states, yeah, if you are just exciting this by the system, some part of the system will also contain these PIs, no. So basically, to summarize in words, YZS contains both, so this is 0 state when you have considered 0 initial conditions, contains both modes due to input and natural modes, okay, and y 0 input contains only natural modes, that is the PIs, okay. So this is the PIs, so this is basically the alpha i's and this is the PIs, very loosely speaking. So therefore, when you are given the YZS and the YZI separately, what you do in order to obtain YF and YN is club together all the alpha i's from YZS, yeah, club together all the alpha I related terms, e to the power alpha I related terms, e to the power alpha I t related terms from the YZS, that will be your YF, okay. The remaining terms in YZS which come from the natural modes, that is e to the PITs, and the ZI, the 0 input terms which are only the e to the power PITs, those sum together, yeah, they will give you your Y natural. So the Y natural is contained both within, some part of Y natural is manifest within the YZS, that is the 0 state, and some part of Y natural is also manifest within YZI, okay. But the YF, the forced part, the forced response part is only exclusive to the YZS, okay. So hopefully this is clear. It is a subtle point, but often we miss this, okay. So I hope that this is clear. So now we move over to a detailed study of the transient responses of different systems. So in an earlier lecture we have seen that in general when Ys is given by Gs times Us, we can write this as the double summation I is equal to 1 to let us say n, and then you have Ri is equal to 1 to di divided by Ai upon S plus Pi to the Ri, counting for multiplicities of those different poles. Okay. So we can expand this is the partial fraction expansion. This is the partial fraction expansion, right. So we can expand this into partial fractions like so, and once we have them expanded in partial fractions, we know how each individual term can be, how we can take the Laplace inverse of each of these individual terms, right. So that will enable us in obtaining y of t, right, by using, because of the linearity of the Laplace inverse operator, we can do that. We have actually assured ourselves. Now if you look at this, yeah, one of the common things that you see here is, of course there will be terms like a upon s plus a in general, and there will be terms like let us say some k upon s plus a squared or cubed and so on and so forth. But apart from these, if you are now a stickler for only real numbers appearing here, yeah, if you do not want to allow this k and a to be complex numbers, we have also seen this, right, in partial fraction expansions, then you will have terms like these where a may be a real number, and you will also have terms like as plus b upon cs squared plus ds plus e, where a, b, c, d, e are all real numbers. So if you do not want to write, for example, if your poles are complex, you do not want to write them separately, right, as complex conjugates of one another, where a's would then be complex numbers and consequently the gains would also be complex numbers, then you just put them together, club them together. We have seen this, right. So this should serve as a strong motivation behind trying to understand how, since the most commonly applied input is the step input, how the step responses of blocks, of transfer function blocks that look like this are actually like. What is our long term goal in pursuing this line of inquiry? We want to find out how the step response of the overall system looks if that can be inferred by just looking at some of these terms, not maybe all the terms in this partial fraction expansion. So we will want to see if we can ignore some of these terms. We will see how and under what circumstances we can ignore them, but we will get to that later by and by. For now, the motivation is, if you are given a Ys that looks like this in the partial fraction expansion form, then if we know what the step response of these individual blocks are like, then we know what the step response of the sums of those blocks will be like. The hope is that if we can stitch together individual responses due to these blocks, then we can sum them together and hopefully we will be able to tell something about the overall conglomeration of those responses, because it is a linear system, right. So because of the linearity property, yeah, whatever is the response due to G1, whatever is the response due to G2, if we sum them together, then we get the response due to G1 plus G2, right. That is the linearity principle. So that should serve as a strong motivation behind looking at the behavior or the responses, the step responses of these types of blocks in particular, yeah, because when we encounter blocks like these which are raised in higher powers, we know that these are basically nothing but the responses of these blocks multiplied by some power of t, some polynomial in time, right. So these turn out to be some fundamental blocks. So with that in mind, now we shall pursue this line of inquiry as to how the step responses behave, and the long form of this goal is, the end game is, here we will see the responses and the effect of the locations of these poles and possibly some of these zeros, that is the zeros of the numerator polynomial, which are zeros of the system, how the locations of these poles and zeros affect the step responses, right. But remember, if you are talking to a non-technical person who does not have any background of controls, that person will be totally flummoxed if you are just talking about poles and zeros of systems. So that person has probably applied a step signal to a black box and has seen the response on an oscilloscope, and he or she understands the system's performance by some layman's terms, or some rather I should say simpler terms, such as you look at a response, how soon it attains a steady value, how soon it rises, how much of an overshoot it has. Forget about the fact that we haven't defined overshoot yet, we will shortly do that, but how much of an overshoot it probably has, right. So these are some of the performance metrics of interest. So as a control engineer, when you are talking to a lay person and trying to find out the requirement analysis, so you are trying to design a system to meet the requirements of your user, the user is not going to tell you that, hey, listen, I want my poles and zeros to be in such and such locations. If they could, life would be a lot simpler for you. Unfortunately, that is not the case. So the user is going to tell you, well, you know, I want this system to behave in this fashion. Now it is your job as a control engineer to translate those layman's terms or those performance metrics that the layman might be specifying into technical terms which translate to locations of poles and zeros, because at the end of the day, it is the locations of the poles and the zeros that will govern everything, as we shall see. Okay. So keep that in mind. With that in mind, we shall now start to look at the response, the step response of first order system. So yeah, before that, there is this ISO that's striking me. It should be IRI, because yeah, you see, with every different degree of S plus Pi in the denominator, the coefficient should also be different. So that was a careless mistake that I missed. Yeah, so it should be AI, RI. It's double subscripted. Okay. So let's look at first order systems, and of course, as I said, we are going to look at only stable systems. So the poles and zeros, not zeros, the poles of the system must always be on the open left half plane, and even if they are on the imaginary axis, as might be the case in second order systems, yeah, if they are on the imaginary axis, then they are non-repeating. All right. So what does a typical first order system look like? Let's say we have a GS given by A upon S plus A. So you might wonder why I am putting this A and S plus A. It will be clear if you think that, let's say, the step response of this, so Y of S is, for example, 1 by S times G of S. Yeah, that is the step response of this transfer function. Now if you want to find out what is the steady value Y of t as t tends to infinity, what is that? That is going to be nothing but S Y of S limit S tending to 0. This is a final value theorem. Remember, because our poles are on the left half plane, we can apply the final value theorem. Yeah, it's always important to bear these things in mind. So then what happens? We have limit S tending to 0, S times 1 by S GS. This is basically my Y of S, replacing this. So therefore I have limit S tending to 0 G of S, which is nothing but G of 0. So if I put this numerator as A, this turns out to be 1. So basically the reason I put this A in the numerator is to normalize. So I want my steady state value of the output to a unit step to be also unity. Yeah, so this A can be anything. You can also put this as K times A, any K times A. Yeah, it won't matter. In that case, the only difference would be your steady state value would be K times 1 instead of 1 itself. So for a unit step, you get an output whose steady value is K instead of 1. But you know, it's basically the same thing, so we really don't care. So let's just look at the normalized version, right? Because we know that for a linear system, if the response due to an input is I, is say Y, then the response due to alpha times U is alpha times Y. Yeah. So similarly, you know, in the system also, if the system G responds with a y, then the system alpha times g responds with alpha times y, because of course whether you are multiplying this alpha with the system's transfer function or with the input u, it really does not matter, right. The multiplication, yeah, is commutative, is associative. So you can say alpha times 1 by s times g is equal to 1 by s times alpha times g. So it does not matter, right. So now having seen this, let us look at what the actual Laplace inverse of this would be, right. We have seen why we have put this a here, so that the steady value is normalized, but now that we have come this far, this is pretty simple really. So y of s is equal to a over s by s plus a is equal to, so I actually do this in a sort of a mental calculation, using some mental calculation instead of using the usual methods of partial fraction expansion. What I am going to do is this, just balancing terms above and below, yeah. So what I am then going to get is 1 by s minus 1 by s plus a. So if I go to the next slide, y of t is equal to Laplace inverse of 1 by s minus 1 by s plus a. This is going to be nothing but 1 minus e to the minus at times the step. So later on we might omit this step. It is understood that it is a causal system, so if you are applying your input at the time instant t is equal to 0, then of course your output for time instance t less than 0 will be 0. You cannot have an output to a system, to an input before the input itself is applied. It would violate causality. So we will assume that it is causal, so later on we will just omit this. For the sake of precision, I have written this 1 of t here, which is the step input. So basically this just says that the output before time t is equal to 0 is 0, right. So what does this look like if I sketch this here? You can notice that this is 1, then this is how your step response would look like, all right. So this is y of t, all right. So what are my variables of interest here? You see, the first thing that comes to mind in a step response for a first order system is something called a time constant, yeah, and this is defined as the time at which the output reaches 63% of its steady state value. Remember, not 63% of 1. If for instance you had k times a here in the transfer function instead of a alone, then your output steady value would have been k instead of 1. So then you would be looking at the time instant at which, for example, let us say this is 0.63. So then instead of 0.63 you would have been looking at k times 0.63, and that would have told you your time constant. So this time constant is denoted by this, let us say this symbol tau. So this is the time constant. Now it might seem like, why bring in this 63% after all? Yeah, it looks like a very odd percentage. It's like something divinely ordained. What is the motivation behind just choosing this figure of 63%? Yeah. Now it turns out that if you see in this particular response, let t is equal to 1 over a. Yeah. Then you see that y of 1 over a is nothing but 1 minus e to the minus 1, which turns out to be 0.63. So this is 63% of the output. So it's actually the other way around. You see, suppose now someone gives you a black box and tells you, look at it as an identification problem. Someone gives you a black box and tells you that you have to identify the pole of the system or the time constant of the system. Rather, let us say the pole of the system is of interest to you, and you can see the step response of this black box. So you apply a step input, a step voltage maybe to an electrical system, and you look at the output signal at the oscilloscope. It will be easy for you to mark out this value of the time instant at which it is 0.63, and you just read off this tau, and the reciprocal of the tau is going to tell you your pole location, right. So it's an easy way to identify, that is the motivation. So we want to have some performance metric, yeah. So for example, here in this case your user will tell you, I want a first order system for me to be designed which has a time constant of 5 seconds. So we assume that the user knows what time constant is. So the user knows that time constant means the smaller the time constant, the faster the system responds, right. So the user says that I am happy with a time constant of 5 seconds. Now you as a control engineer would immediately translate that to mean that the user wants a pole location at minus 0.2, right. So that is why this weird sort of a figure of 63% emerges for a first order system. The second thing that people talk about is rise time, yeah. So basically remember, as I said, your user is not well versed with control systems terminologies like poles and zeros and stuff like that. So they will specify the system using these terms like time constants and rise time, okay. And gradually over time you should also get used to these terms and specifying system performances or performance metrics using these terms, and inherently, implicitly, as a control engineer you will also know what that means in terms of pole and zero locations, okay. That is the goal. So what is the rise time? Again, this is a metric of how fast the system responds in some sense. So time taken by the step response to go from 10% to 90% of steady state value, yeah. So how do you do this? Simple, just take 1 minus e to the power at1 is equal to 0.1. So this is the time at which you have attained 10% of the steady value, and take the second equation as e to the minus 80, sorry. So 82 is equal to 0.9. Now clearly from these equations you can see that e to the minus 81 is equal to 0.9 and e to the minus 82 is equal to 0.1. So if you divide these one by the other, you get e to the minus a t1 minus t2 is equal to 9. Now you take the logarithm on both sides and you will see that t2 minus t1 turns out to be 1 by a natural log of 9, which is approximated by 2.2 by a, okay. So the smaller your a, yeah, the smaller your a, the closer your pole is to the imaginary axis. Notice very carefully, the smaller your a, of course a is positive. So because let me mark here, because I said it's a stable system, so a is positive, yeah. The smaller your a, the closer your pole is to the imaginary axis, the larger is your rise time. Similarly here of course there is a clear reciprocal relationship, smaller your a, the larger is your settling time. So these are both metrics of how fast your system responds to a unit step, right. So the farther you go from the imaginary axis insofar as your pole location is concerned, the faster is your response of the system. And the final parameter we are going to look at is settling time. So this is the final parameter we are going to look at for a first order system, and then probably in the next lecture we are going to look at second order systems, step responses and the transient behavior, right. So here we have settling time. So how does the settling time play out, or how do we define this? This is nothing but the time taken by the step, actually it could be for any other symbol also, you have to then redefine, you have to obtain your Laplace transform or inverse Laplace transform according to that input that you have defined. So for the step response here is what we are concerned with. So we will say that time taken by the step response to reach within 2% of the steady state value. Again this is easy to obtain, so we just say 1 minus e to the minus a ts is when you have reached 0.98 of 1. So then, And remember, it will not change if you change this transfer function from a to ka here, yeah, because then you will have k on both sides, so they will cancel out. So it's basically the calculation still remains the same. So from this you can obtain this computation through computation as 1 upon a times ln 50, because 1 minus 0.98 is 0.02, which is 1 over 50, right. Once again, this you can approximate as 4 upon a, alright. It is actual value is of ln 50 is around 3.9, so we are approximating it as 4. But the key message to be taken home from all of this is that all of these parameters, the settling time, the rise time, the time constant, they are all inversely proportional to a, which tells you that the smaller the value of your a is, the more sluggish your first order response is going to be by whichever metric you analyze it, whether it's the settling time, whether it's the rise time, or whether it's the time constant, okay. So hopefully with that we've understood, right, that what all of this where we are trying to play at. So unfortunately a first order system only has, or rather fortunately we might say, only has one parameter to play around with, which is the a, because the gain, as we've seen, if we make this k times a, it doesn't really affect the response much. So obviously everything, every performance metric will be governed solely by a. So if you want your response to be faster from the perspective of settling time, from the perspective of rise time, from the perspective of your time constant, yeah, you better make your a as large as possible. Before we conclude, a quick word about the difference in character, and this will be clearer when we discuss second order systems, about the character of settling time and rise time. Apparently both of these are telling you about how fast the system responds to a unit step. So you might wonder, why are we introducing suddenly this rise time and settling time separately? Why can't we just have one metric? You see, there's a difference, and the difference is this: the rise time is telling you how soon the system is rising from 10% to 90%, okay. So it's basically right at the initial phase, immediately after you've applied the input, how soon your system responds. On the other hand, the settling time tells you, yeah, how soon you are going to approach this steady value. Now for a first order system, we see that these probably entail the same thing, that play around with a, try to make a large enough, that is shift the pole more to the left half plane, the real pole to the left half plane. As you push it further and further to the extreme left, the faster is your system's response. In the case of second order systems, interestingly we will see that rise time and settling time do not necessarily convey the same kind of performance metric. So that's something to look forward to, and in a second order system we will have more parameters to play around with, that makes things more interesting and more involved. So hopefully that will be some interesting content for the next lecture. Till then, thank you all.